nickname. Just to help you at the end. It's not. I'm not going to stalk. Okay. Okay, so last time we talked about spectroscopy. So the only way we have to learn about the universe and stars is to collect light. Okay, so light is a great informant. And in the beginning of 20th century, thanks to modern physics, right, they developed what is called spectroscopy. So you have light, for example, coming from a star. You're going to use a prism and you're going to split this light into its colors or wavelength. Okay, so you see the light comes from the inside of the star, which is the core, right? And light will escape. It can take 100,000 years for light to make it through the atmosphere. Okay, so here you have a prism. You split the light into this continuum, so all the colors of the rainbow, and you see that on top of it, you can see what is called absorption lines. And the explanations for those absorption lines, I have allergy, okay? I'm not sick, I'm always stuffy. But allergy is getting better because it rained yesterday. So anyway, the why of those absorption lines was explained by the scientist Saha and then Cecilia Payne. Okay, so we talk about that. So anyway, you're going to see this QR code because you are missing some wavelength. So we call that a wavelength deficit. Okay, sometimes you have a small deficit and sometimes you have a large deficit. Okay, so by looking at those absorption lines, you can tell what is inside the atmosphere. So do we have calcium? Do we have magnesium? Do we have oxygen? Plus, if those lines are moving, okay, so if instead of being here, all of a sudden it's going to be shifted to the red, that means the star or the galaxy is moving away from you. If the star or the galaxy is moving toward you, those black lines will be shifted to the blue compared to what we expect in the lab. So, for example, if you have the hydrogen line here, let's say this is hydrogen, if it's shifted to the red, that means the galaxy or the star is moving away. It's shifted to the blue shifted, it's moving toward us. So that's how they discover in 1920, if I remember. Edwin Hubble discovered, but not only him, discovered the expansion of the universe. Because when you look at the galaxy, so you don't need to have a spectrum from a star, you can get a spectrum from a galaxy as well. All those lines here were shifted to the red. Farther you look, more shifted they were, which means the universe is expanding. And nowadays, we know that the universe is accelerating because when we compare the shift back then to the shift now, we see that the universe is expanding faster than it was before. So all this is because we know how to analyze those spectra. And again, it can come from a galaxy or it can come from a star. Okay, so let's review for the pop quiz here. You see, if this was the sun, you see that the peak wavelength, okay, is in the green. The peak wavelength is the color that you get the most. Okay, so the sun is going to emit a lot of many green photons, and not any kind of green, this green. So by looking at that wavelength, we call that the peak wavelength, we can know the temperature of the sun, at least this temperature here, which is about 6,000 Kelvin. So by using the peak wavelength. So this is called Wien's law. So if I ask you for the pop quiz, this is called Wien's law. It's a very easy relationship between the peak wavelength and the temperature. Smaller is the wavelength, larger is the temperature, because you get a blue star which is very big and very hot. If the wavelength increases, so you go to the red, okay, so that means the temperature will go down because the star is small, so it's not squeezed as much. Okay, so this is called Wien's law. In 1900, you have Max Planck, who was able to derive this curve. Here we call that the black body curve. All it's going to tell you is say it's, for example, if you take the sun, it's going to have a lot of green, a little bit of blue, but not that much, little bit of green, but not that much, a little bit of UV, X-ray, gamma ray, almost nothing. And on the other side, you can have a little bit of infrared and microwave. Okay, and there is in physics, they found that if you find this area here, so the area under the curve, you're going to find the luminosity of the star. So what's the luminosity? The oomph, the power, how much energy is produced per second. Okay, so this is called luminosity. So this is the area here under the curve. So of course, that will be the luminosity if the star is close to you. As you move the star away from you, it's not that you are moving the star away from you, but if the star is farther away, you cannot find its luminosity. You're going to find its brightness, how bright it appears to be. But if you know the distance, then you can find the luminosity. Okay, so if I have in my hand a flashlight, if it's close to me, that will be the luminosity, the oomph, the power output in watts. And as I move the flashlight away from me, what I'm going to collect here with a special sensor, that's going to be the brightness. And there is a relationship between luminosity and brightness. As you move away, it's going to be dimmer. Does it make sense? So if I know how bright it appears to be, and I know the distance, I can find the luminosity. So that was all developed with modern physics. So that's when it became astrophysics, right? So I don't know if I have a video that someone sent me, which is cool. If I am, let's see if I can find it. No, I'm not in the right folder. Okay, so just to give you an idea what luminosity is, it's the watt. So for example, if you have a light bulb, usually you're going to have 40 watt, 60 watt, very, very bright will be 100 watt. So that will be the oomph. Okay, light bulb is like a star. It's a black body. And so this guy built a 20,000 watt. And our sun is 10 to the 26 watt. So not to do at home. So I don't know if you can see. First, it's going to be red. So you don't want to touch it, right? It can burn, but it's not as hot as white. So first it's going to be red hot, and then it's going to be white hot, and then it's going to be blue hot. Okay, so the color depends on the temperature. So it's going to get hotter and hotter and hotter. So all that energy is going to turn into heat and light. So it takes time. It has to warm up. So you see it's going to change color from red is going to white. So white is hotter than red. You have that with a stove, for example. So getting whiter and whiter and whiter. Come on, come on, come on. Oh, of course. It was not playing. Little by little. This is a 20,000 watt light bulb. Just to give you an idea. And you see the energy is going to spread out in 3 dimensions, but it's still very impressive. So what do we call luminosity of a star is the watt. Okay, the power, the energy output per unit second. So it's called the power. Okay, so that's just to review. so you know what to say for the pop quiz. So back then, they didn't have digital technology that we have today. So they had to use what we call the plate, a photographic plate, and it was made of glass. So you will put that, attach that to a camera, and then with a prism at the end of the telescope, and that's what you will get. Which is very hard to handle because, of course, it's very breakable. So, okay, so this is called spectroscopy. We talked about, there was a question on the pop quiz, Ali Jan Cannon. She's the one who cataloged all the stars available at the time, 100,000 of them, and she cataloged them into classes. So it's called classification. So spectral classes. And those classes are named after oh, boy, fine, guy, girl, or guy, depending on your preference. Kiss me lovingly. And then they added tenderly, T, and then Y. Okay, so we talked about the HR diagram. We're going to talk about that again. So I'm not going to go over that. This is the scientist who was able to make the connection between absorption lines and temperature using physics, and she put everything together here, apply that to stars. Her name was Cecilia Payne. Okay, so we talked about that, we did that. Okay, so I stopped here. So now it's much better than before. We have very nice HR diagram. So this here is called the main sequence. So any star that is burning hydrogen into helium, okay, will be plotted on that line. Okay, so it's like a line, it's a main sequence line. You see the size will change, of course, because larger star will have more mass here, so they will be blue star. That's why the gravity is squeezing them more, so they have a higher metabolism, but it's not drastic, the change in size. So here you have cold star, they are red star, and somewhere over there you have our sun, which is like a white star. On the x-axis, we talked about that, you have the classes. So you have oh, boy, fine, guy, kissed me lovingly. And now we have also the temperature of the stars. And the y-axis, you have the power output, the luminosity. And you can compare that to the sun. So if the luminosity of the sun is 1, you take one step here, that will be 100 times more luminous than our sun. And then you multiply by 100 again, which is a step of 2, so it's a log scale, crazy, crazy, crazy luminous. Okay, so that's how the HR diagram works. It's kind of backward because here this is cool and here this is hot. And then when the star is done burning hydrogen into helium, it's the beginning of the end, right? It's like you hit 60 years old, you start to worry a little bit, right? So for a star, it's going to be the same thing. Its metabolism get broken, so it's not as efficient to burn fuel. And because there is no more hydrogen, it's going to turn to helium. So our sun, when it's going to be done burning hydrogen into helium, it's going to move in this area here. So red giant. So our sun will become a red giant, okay, 4 billion years from now. And then, see, it's going to be swollen. So even though it's going to be still very cool, so it's cooler than some star here, so it's going to be cooler, but because it's big, it's going to be more luminous because of its size. So it's going to burn hydrogen into magnesium and then carbon, and then it's going to run out of helium. What's going to happen? It's going to be even hotter, right? Because the core will squeeze even more. So we're going to get magnesium, other element. So it's going to move somewhere there. At that moment here, the sun will burp out its outmost layer. It dies. So it cannot burn fuel anymore, and it will become a white dwarf. So it will be like a exposed core, right? So the core will be exposed, and it's gonna not be as luminous. It's still gonna be very hot, and it will cool down and become a white dwarf. Okay, but that will be the main sequence. If you have a very, very hot star, it will do the same thing. When it's going to run out of hydrogen, it will become a super giant, which is like Betelgeuse. And then sometimes it can oscillate to be a super blue or blue giant like Rigel. So it can go back and forth. And then it will end up as a neutron star or a black hole. Okay, so I try to summarize everything. Let's see, like in a nutshell. Okay. So you see here, our sun starts here from a nebula, gas and dust. Okay, so we're gonna have the sun. The sun will burn hydrogen into helium. At some point, it's gonna run out of hydrogen. It will become a red giant, which is cooler but bigger, so more luminous because of its size. And then it will burp out its outmost layer in a beautiful planetary nebula, and what will be left behind, it's a dead corpse. It's called a white dwarf, and no fusion. There will be no fusion anymore. So it's a white dwarf. It's not really a star because there is no fusion. It's dead, and it's gonna dim away. If you have a big star, okay, it depends, what you begin from. So if you have enough stuff to make a big star, you're gonna get a blue star that will inflate in a red supergiant when it's gonna run out of hydrogen. Then it's gonna end up as a supernova, and you can have a neutron star or black hole. Okay, so just summarizing it. Can you not be on your phone? This is very annoying. Okay, so here you have examples. I just want to show you a short video. Okay, short video. Nice video. I think it's this one.
When you look up at the sky, you'd be forgiven for thinking that all stars are the same. But that's far from the case. In fact, there are lots of different types of stars, from brown dwarfs to white supergiants, that can be categorized according to their mass and temperature, as in this Hertzsprung-Russell diagram. Red dwarfs are small stars with temperatures cooler than that of the Sun. They are the most common stars in our galaxy and are less than half of the mass of the Sun. They burn slowly and so live for a long time relative to other star types. They are positioned below the main sequence on the Hertzsprung-Russell diagram. Red giants are cooler than the Sun, so they have a red-orange tinge to the visible light they emit. Living up to their names, the largest red giants may be over 100 times the size of the Sun. Red giants are stars near the end of their life. They come above the main sequence on the Hertzsprung-Russell diagram. Stretching across the upper regions of the Hertzsprung-Russell diagram are the supergiants that cover a wide range of temperatures. These stars are truly enormous. Placed in the centre of our solar system, the largest of these, such as the red supergiant Betelgeuse in Orion, would engulf all the planets out to the orbit of Saturn. Like Betelgeuse, Rigel in the Orion constellation is also a supergiant, but it is a blue-white supergiant. Supergiants are high-mass stars near the end of their life. When a supergiant dies, it explodes as a supernova, then shrinks to become a black hole. There is a group of very faint but hot stars in the bottom left of the Hertzsprung-Russell diagram. These are called white dwarfs and are so faint that none is visible to the naked eye. They are very small and dense, formed when a main sequence star reaches the end of its life. White dwarf stars gradually cool over time until they no longer emit light. The smallest, dimmest, and coolest stars are brown dwarfs. They are at the bottom end of the Hertzsprung-Russell diagram, at the lowest part of the main sequence. They are also known as failed stars and are very difficult to detect, as they do not have sufficient mass for nuclear fusion to occur. The main variables in star formation are mass and temperature. It is these which produce the wide variety of stars we see, and many we can't.
It's a very nice video. I don't know if you know this, it's called the Open University. And as you can hear, it's a British accent. So the Open University is like a university, you can take classes online for free. Some of them are free. And I took a class there, like in a Python, I think. So it's like Coursera or EDX. So it's free classes that you can take. You don't need to have credit, right? You don't need to get credit. Just for your own interest, you can take those classes, right? Just for free, which is amazing. So anyway, that's a tangent. So it's a very nice video. Okay. So the stars here will come in different sizes and different color. So you see, all star will be very large and that will be very small. Okay, so again, the mass is the stellar property that will define everything. Everything but distance, obviously, and chemical composition. So you see the temperature is about proportional to the mass. So for example, here you divide by 2 the mass, temperature will be divided by 2. Luminosity means the oomph, right? The power, the watt. So that depends on the mass to the 4th power, which means it's like a question in the assignment, but you multiply the mass by 10, the power will be multiplied by 10,000, 10 to the 4th power. Why? Because if you increase the mass, gravity is going to squeeze more the core, so the metabolism is going to increase. You're going to fuse faster. Okay, it's like when you are young, you have a high metabolism, right? So you can eat crap. But when you get older, you have to be careful because insulin, you get what is called insulin resistance, and your metabolism is not that great. Okay, so here if you have a large mass, you're going to have a high metabolism. It goes as the mass to the 4th power. And then here you have the size. As you increase the mass, you increase the size. And it's also proportional to the mass. And then you have life. Okay, so the life is inversely proportional to the mass to the 3rd power. So if you multiply the mass by 10, your life will be divided by 1,000. So if you have a very, very large star, it will only live for a few 100,000 years, a million years. If you have a star like our sun, it's going to live for 10 billion years, and it's half of it. So we have like 5 billion years to go. If you have a very small star, so these are very greedy. They don't like to use their fuel quickly, right? They go very, very slowly. They have a very, very slow metabolism, so they last forever, trillions of years. So these are called red dwarf. And those who were made just after the Big Bang, they are still chilling. chilling around, because the universe is 14 billion years, and those they can last for trillions of years. So our sun G star is here. It's gonna last for 10 billion years. If you have very, very large star, they're gonna last for a few million years or even less. Okay, so let's keep going, but I will make where is my HR diagram? I'm gonna leave the video for later. So let's talk again about luminosity versus brightness. So it started by a Greek guy, Hipparchus, very famous. So that was like 200 BC. I don't know if I can pull out his page here. So you see, he lived in what is now Turkey. But at the time, it was the big Greek, it was not really an empire, but after Alexander the Great, he was able to conquer Greece, obviously, because it was Greek, but also Turkey, Iran, which is Perse at the time. So he had a huge empire, but he was broken into little states, right? Not getting along that well, but they call that the Hellenistic states. So it means Greek. So at the time, they were all Greek. So anyway, around 190 BC, he's also considered as the father of trigonometry, and he was able to catalog stars, but there was no telescope at the time because Galileo was not here yet, right? Obviously, but with the naked eyes, he started to catalog the stars. He even find out that the equinox was changing with time. Remember, now we are in Pisces, and then we'll get into Aquarius. Peace and love. We're not there yet, but anyway, this is because the Earth is precessing. So anyway, so his name is Hipparchus. Okay, so Greek, and he's the first one to decide to catalog the stars according to their apparent magnitude. So at the time, they didn't do the computation, okay? They were not able to find what, for example, per unit area. It was just based on the eyes. But nevertheless, he cataloged the stars according to the apparent magnitude, which is like brightness, how bright they appear to be in the sky. And he had a very special system. So the brighter star was given a 1, and the fainter star was given a 6. So brighter will be smaller number, fainter will be larger number. So it's kind of counterintuitive, but that's his choice. So Sirius, for example, here is the brightest star in the sky, and that's going to be 1. And if you go this way, so these are not stars, okay, but the numbers get smaller. Venus is very bright, so it's going to be brighter than Sirius. Obviously, the moon is going to be even brighter, and the sun even brighter. But this is relative to Earth. And then now we know that you can go the opposite way, so that will be fainter. So now we know that this is a log scale. For those who know math, right? Log scale means you go one step and you're going to multiply by a number. That's the log scale. So when you go from 1 to 2, in this system, you multiply the brightness by 2.5. So when you go from 1 to 6, you multiply by 100. You don't need to know that, just to, if you're interested. So anyway, he was really the first one. And then came astrophysics, right? And now they were able, with astrophotography, they were able to find the brightness of stars, how bright they appear to be. Okay, so they used the area under the black body curve, and they were able to find how bright they appear to be. So it means watt per unit area. So this is called apparent magnitude, is qualitative, and this is quantitative. Okay, so it's both of them, it's how it appears to be on Earth. So let me explain here. Let's say this is the sun, right? And you have a sensor, and this is my sensor. I'm gonna, let's say I'm able to find the luminosity. So that will be the luminosity, the real watt, oomph. So that's called the luminosity. But as I move away, 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 you see it's gonna be dimmer. So that here is what we call the brightness. Why is it going to be dimmer? Because the same amount of energy is going to spread out over a larger area. So of course it's going to be dimmer. And it's going to follow what we call the inverse square law, which means if you multiply the distance by 2, the amount of photons that you get will be divided by 4. If you multiply the distance by 3, so 1, 2, 3, it's going to be divided by 9. Makes sense, right? Because it's spreading out. Okay, so if I have a bucket here, this is my star. I'm collecting all the photons. Boom, 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 boom. I'm very close. That will be the luminosity. I multiply the distance by 2. I'm going to have less photons, 4 times less. I multiply distance by 3, 9 times less. Okay. So anyway, apparent magnitude is how bright it appears to be to your eyes when you are on Earth. If you do the math, it's going to be called the brightness. Now, after 1900, we were able to find the luminosity, so the oomph. So it means if you know how bright it appears to be, then you can find how bright it is in reality. So that will be the watts. So then they define something called absolute magnitude, which means it's also qualitative, and it's just how bright is a star if they are all at the same distance. Okay, so let me give you an example so you understand. So let's say you have a 1,000-watt light bulb, like the one I showed you before. If you are close to it, it's going to be the luminosity, the oomph, the energy output. How much energy you have here leaving the light bulb in the form of radiation. So that energy is going to spread in 3 dimensions. So if you move away now, okay, so this is Earth, let's say. Now, if your distance is multiplied by 2, it's going to be divided by 4. So now you're going to see a 250 watt. So that will be called the brightness or the apparent magnitude. This is the luminosity or the absolute magnitude. Do you understand? It's not that hard to understand, right? So that will be 1,000 watts, the total amount of energy being burped out. And as you move away, that energy is going to spread out over a large area, and it's not going to be as bright, obviously, it's going to be dimmer. So how dim it appears to be, this is the brightness. How bright it is, really, it's the luminosity. Or qualitatively, this is the apparent magnitude, this is the absolute magnitude. Same thing here, if you have 1,000 watt, and now you move away, the distance is multiplied by 10, of course it's going to be very dim. So 10 square is 100, so you divide by 100, you get 1,000 watt. If you like math, you have this relationship, but you get the idea. It works like gravity. Gravity works the same way. If I am, let's say, 400 pounds on Earth, 400 pounds on Earth, and I move at a distance twice as much, twice, so it's 2 to the 4, 2 to the 2 square is 4, so I will be only 100 pounds. Okay, so let's take an example. Here is the best example I can find. The sun is in reality 4 times 10 to the 26 watt light bulb. So it means 4 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. That's a lot of watt. But because we live far away, thank God, 196 million miles away, it's not going to be as bright. Good, because otherwise we'll be fried. And we get here only 1000 watt per square meter. So if I go outside and the sun is just above my head and I have a 1 meter square on the ground, I can collect 1000 watt. And ideally, I should be able to turn that 1000 watt into electrical energy, for example. But it doesn't work that way because the sun is never exactly above your head, first of all. Second of all, it's not very efficient. The solar cells are not very efficient, so we're going to get less than that. But this is ideally. So this is called the brightness. You see, it's 1000 watt per meter square. So you have a square here and you collect 1000 watt, which is joules per second. So how much energy flowing per second on 1 meter square. And this is in reality. So again, this is called the absolute magnitude or luminosity. This is called the apparent magnitude or brightness. I'm trying to make it as clear as I can for non-science measure. Did I make myself clear? Yes? Okay, good. Okay, so that's the story. Here, if we use a system of Hipparchus, you see the number here will be the apparent brightness. So Sirius here is the brightest star that we have. Betelgeuse you can see with the naked eye, right? High-gel you can still see it with the naked eye. Okay, so Sirius here, remember, is the brightest star in the sky. You see the dog, you can clearly see a dog. So it's the star of the color here. So that will be the apparent magnitude. But if you take all the stars here at the same distance, so then you get the real stuff. So then you get what is called absolute magnitude. So Sirius looks very bright because it's very close. So if you put all the stars at the same distance, all of a sudden Sirius is not as bright. So what do they say? The love is in the eyes of what? Of the one who have the eyes, right? So it's everything is relative. So relative to Earth, of course, Sirius is the beloved brightest star. But if you put all the stars here at the same distance, it's not that bright. So this is apparent magnitude, this is absolute magnitude, because they will be at the same distance. In the eyes of the person, of the eyes of the beloved, so anyway, you know what I mean? So Aldebaran also 0.85, you can see it with the naked eye. Okay, Procyon also can be seen with the naked eye. So smaller the number, brighter. So it's, I think Procyon is the second brightest star. Okay, so if used to be when I was teaching astronomy a long time ago, we had to rely on textbook because there is no internet. I mean, of course, there was internet. I'm not that old, but you could not use so much as I am using today. So students had to use their textbook here. And at the end of the textbook, you can see the apparent magnitude of stars. Okay. Okay. So that's for those. who are interested, it's a log scale. Okay. So what is their absolute magnitude? That will be if you place all the stars at the same distance. Okay, I talk a lot about that. Okay, so physics give us a way to find luminosity of a star, and it depends on the temperature to the fourth power. Okay, so it's called Stefan-Boltzmann law. So it means if the temperature is multiplied by 2, okay, the luminosity will be multiplied by 16. But it also depends on the size. So luminosity mostly depends on the temperature to the fourth power, but it also depends on the size. So temperature is like mass. So again, luminosity is the oomph, right? The energy output, and it depends on the temperature to the fourth power. Depends also on the size, but if it's on the main sequence, it does not really matter. It's when they are leaving the main sequence that it does matter. Okay, so again, that will be Wien's law, HR diagram. So I found a very nice video. Hi, HR diagram. No, I think we did this one. Okay, this one is super cool. And it's based on real data collected by Hubble Space Telescope. So it's a very nice one.
This is a Hubble Space Telescope image of the crowded core of the globular cluster Omega Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort these stars out by color, blue on the left and red on the right. Next, we'll sort the stars according to brightness. The brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When the fuel starts to run out, they expand to become red giants. They find a new source of fuel, helium, and burn blue hot. But even that runs out. They end up burning out as white dwarfs. Based on images for the Hubble Space Telescope, we've assembled a true plot that is a snapshot of the life history of stars in this ancient cluster.
So you see how it's done? You have a cluster of stars. They are all linked together by gravity, glued together by gravity. And then you can plot each one of them on the HR diagram. Okay, any question, let me know. So this one is a nice diagram again because you can see the relative size. So on the main sequence, you see that the size is not going to change that much. The size become problematic only when they're going to leave the main sequence because they don't have hydrogen to burn anymore. So HR diagram is the most important diagram in astronomy. So it's like the periodic table in chemistry. So you have, it's called the Hertzsprung-Russell because both of them published that diagram in the 1920, something like this. So this is called the HR diagram. And again, you have luminosity, so power, the power output. And here you have the temperature. Okay, so this one is my favorite one. It's amazing. It's very nicely done. What I want you to remember is the quote from Blade Runner. Twice as bright, half as long. It will last half as long. So if you multiply the luminosity, so how bright it is, by 10, your life of star will be divided by 10. And you can see that here. Okay, so if you take that star here, right? So 10, luminosity is 10, which means 10 times brighter than the sun. So this is the sun, luminosity is 1. So they like to compare luminosity to the sun luminosity. So you multiply by 10, life will be divided by 10. Okay, so it's exactly what you see here. You go from here to there. One step means you multiply by 10. So if luminosity is multiplied by 10, the life is divided by 10. You can see here, life of Sirius is about 1 billion years. And you divide by 10, that's going to be 100 million years. Now, if you go opposite, so if you divide luminosity by 10, so divide by 10, you get 1. So that will be our sun, 10 times less luminous as Sirius. The life will be multiplied by 10. And you see, the life of the sun is 10 billion years. And then you divide again by 10. So now you are here. So 10 times less luminous than our sun. The life again is multiplied by a factor of 10. So instead of living for 10 billion, you're going to live for 100 billion years. Okay, so the light that has twice, for example, the brightness will have half the life. So here, those here, they're going to live for trillion years. And as you go this way, you see this is the sun, 1 times the mass of the sun. Here we get to 60 times the mass of the sun. So they will have a very short life, like 1,000,000 years. And 1,000,000 years for a star is very young. So this is live hard and die young. Okay, so the HR diagram, so it means luminosity versus temperature. Oh, that's a good question for the pop quiz. Luminosity versus temperature. You have the main sequence, you have the giant, right? When they are done burning the hydrogen, red dwarf, it's a corpse, it's a dead corpse, it's dead, no more fusion. And a white dwarf here, it's dead. Red dwarf are the very, very small stars that are very, very greedy. They like to save. It's like people. Some people, as soon as they have money in their pocket, they need to spend. Some people, they don't like to spend. They are very greedy. Not greedy, but just saving. So red dwarf, they like to save. Okay, and that's going to tell us what's going to happen to our sun. So I think I have a video about that, right? So it's going to run out of hydrogen. It will become a red giant. And then it's going to be not as efficient. So temperature will increase here. Okay, so then it will burp out its outmost layer. It will expose the core. So it's still going to be hot, but it's small. So not as luminous. And it's going to dim away. And so much that at the end we call that a black dwarf when we cannot even see it anymore because so cool it is. So I don't know if I have a video. I know I have a video. It's just that my folder, I don't know where it is. Ah. I think it's here. Look at that. I'm organized now. So you see the sun. So it starts from a planetary nebula, from a nebula, from a nursery. So this is the sun burning hydrogen into helium. So it's a main sequence star. And then, of course, I forgot to play it. Okay, play. So it's going to become a red giant. Okay, so luminosity is going to increase because of the size and become a white dwarf. And that's it. It's going to dim, 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 dim. And it's become a black dwarf. We won't be able to see it anymore. Isn't that cool that we know so much about what's going to happen? Oh, this one also is very cool. Because you can see the relative size. Okay, done. 7.3. Almost done with these units. So what I was telling you is that the luminosity, so the power, depends on the mass to the fourth power, or temperature to the fourth power, not so much on the size. Except when the star is going to leave the main sequence, then the size matters. Because you can have a red star outpowering a blue star because it's so big. Okay, so then star matters. It says, so yeah, let's see if I have something about size. Now that's a very cool
Let's
video.
instead witness a series of size comparisons, starting with the Earth, where objects are shown precisely to scale. We will zoom out from the scale of the Earth until we get to one of the biggest known stars. Prepare yourself to be astonished at just how much bigger than our Sun stars can really get. Here we go.
And you have the music. Instead, you are falling asleep over there in the back. I see you. So it's a log scale. So the steps, I think it's a head-worth. Sirius is blue.
It is astounding to think that once this visual comparison is complete, we can no longer even see our Sun. That's how significant the disparity is. We stopped at Canis Majoris, a red hypergiant star, which is so huge that if we replaced our star with this one, it would engulf every planet in the solar system up to Saturn. And yet, this is not even the largest star that we know of. The current title belongs to UY Scuti,
So it's a very cute name.
which has a radius that is even 20% larger than Canis Majoris. Will we ever find even larger stars? How large is the largest star in the entire universe? Is there some fundamental principle we can discover that can elucidate the formation of these hypergiant stars? Perhaps one day we might learn the answers to these questions.
So you see, I don't think you understand how lucky you are to be in the digital age, because that was not available to us when I was a student, right? So here you can really visualize here's another picture where you can see the relative size. So and then I have a very good video, but I don't know if we watched it already. Anyone
Let's
remember?
instead.
Not this one, not this one. This one. Did we watch that?
Have you seen those videos? Interesting about Arcturus is that it is.
Do you remember? No? Gabriel, do you remember? Did we watch it? We didn't? No? It's a super cool video. We don't have time now, but we will watch it. So the size matters, right? So for example, if you have a volcano, you see the lava here is red. So it's not that hot. Red is not as hot as blue, it's not as hot as white. But if you increase the area, you're going to increase the amount of energy, and it depends on the area. So it's going to be proportional to the size square. Okay, you multiply the area by 3, it's going to be 9 times more luminous. So much so that even if the lava is not that hot, he still needs to wear some kind of suit here to protect him from the radiation. So it's very, very, very luminous. So it can burn you from the radiation, not because of the temperature, but because of the size. Okay, so luminosity depends on the temperature, but also on the size. And the size matters only when a star has left the main sequence, when it inflates like a red giant, super red giant, hyper red giant. They can be monsters. So here, same thing, if you cover New York City here with some kind of, what is that? Something very hot here, it's not going to be that hot, but if you increase the area, of course, it depends. The luminosity not only depends on the temperature, but it depends on the size square. Okay, so if you take Betelgeuse has the same temperature as the sun, about, but because it's 1,000 times larger, the 1,000 square is 1,000,000, so the power will be multiplied by 1,000,000. Okay, because it's a square. So sometimes, if the star does not belong to the main sequence, what matters is the size. The size matters a lot. So even though this one has the same temperature as the sun, because it's so big, it's going to emit a lot of radiation because of its size. And the relationship is square. See, if you put Betelgeuse here instead of our sun, we're dead. We can't. It goes up to Saturn. So the sun is perfect. Okay, so we finish that. Next time you have a pop quiz.